Hello and welcome to another video on basic fiber optics. In a previous video, I explained how a grating-based optical spectrum analyzer works. Now essentially, just to recap very quickly, you send a beam onto an optical grating which diffracts the incoming light into different orders, and because the angle of diffraction depends on the wavelength coming in, you can sort of split up the signal and then measure each wavelength individually. And so the resolution of that OSA that you get will depend on essentially how closely spaced these grating lines are, or more appropriately, how many of these lines get illuminated by the incoming beam. So the more you illuminate, the sharper line you get here and the better resolution you have. Now there is another approach to building optical spectrum analyzers that I want to show you today. And essentially it works a little bit more like an electrical spectrum analyzer that you may be familiar with if you've done electrical engineering. The idea is that we have an incident laser here that we want to measure. We send it into this optical spectrum analyzer here. Now inside of this, there's a highly stable reference laser that we merge together with the incoming signal and then send on to a photodiode. So the idea is that when these two lasers hit the photodiode at the same time, they are going to interfere and generate this time-dependent oscillation in the measured power. This can then be sent into what's essentially an electrical spectrum analyzer, which uses various signal processing techniques like Fourier transforms and whatnot in order to generate a frequency spectrum. And so because the wavelength, or rather the frequency of the reference laser is known, then if you measure a certain oscillation frequency here at the ESA, then you can back calculate what the frequency of the incident laser was, like this. So let's go take a look at the actual device. Okay, so I've turned on this distributed feedback laser that we discussed in a previous video and sent the input into this high resolution optical spectrum analyzer here that works on the ether principle I just explained. So as you can see right here, we have an extremely narrow peak that's being measured here. And I'm not sure if you can make it out, but right now the whole span here is, well actually each one of these divisions here is 50 picometers. And you can see that we have a, well, we could call a point-to-point resolution of 0.04 picometers. That's essentially the separation between two individual measuring points here. And essentially the actual resolution of the OSA will be determined by the line width of the internal laser. So what we're seeing here is actually not just the line shape of the laser we're measuring, it's actually the convolution of the line width of the measured laser and the internal one in here. If you want a bit more of an explanation of that, you can check out my video on laser line width. And just to prove how much better resolution this one has, we can actually compare it to a grating-based OSA that I have set up over here, measuring the exact same signal. So put a coupler right after the laser, splitting it into two branches. Then one went into the high resolution OSA that we just saw, and the other one goes in here. You notice that the settings are exactly the same here. We have the same sort of measuring range here, but you can see that this peak has much more round. That's simply because the grating used to split up these wavelength components spatially will cause it to each, well, even if you had a perfect laser sent in, you get like a smeared out spot. That smearing out sort of makes the line width look much larger than it actually is. So just to compare again, let me move the camera back. You can see this is indeed much more narrow. You can see much finer details here compared to the other OSAs. So if you had two lasers very close to each other and you want to measure the wavelength difference, this would be a much better option compared to the other one. And just for good measure, let's actually try and zoom in just a little bit more. So maybe I'll reduce this to 10 picometers. There we go. So we can see it's still quite narrow. And I think we can even go a bit further. Let's see how small we can get. Oh, that was a bit too much. Let's go to maybe 5 per division or something. It's a bit better. All the way down to 1. And there we go. So here you can really see how good the resolution of this device is. And again, part of the reason why this works is that it simply operates on using Fourier transforms. So if it takes a really long trace with lots of data, then it should be able to measure really small changes in frequency. Alright, hope that is helpful. I'll see you in the next video.